Hello, everybody. So what we're going to be looking at today is going to be section 6.1 in your book, vector fields. So, of course, as you can see, we're in a new chapter. And as always with a new chapter, what that probably means is we're on to a new topic. And also, the first lecture is easy, but has a lot of definitions. That's probably going to be the case here, right? This is an introductory section. So the homework's very easy, but also vocabulary is something we have to get used to. So the new topic is going to be vector fields, obviously. So this is a whole section on vector fields. This is the last chapter that we cover in this class. And depending on who's teaching the class, they either cover some of it or all of it or something. Okay. The more of this you get, though, the better off you'll be going forward in your mathematical career. Just because um, this stuff gets used in physics all the time, like all the time. So yeah, hopefully some of this will stick with you. So let's go ahead and get started. So what we're going to learn how to do is recognize what a vector field is, match them up with their functions, and so on. We're going to need to sketch them ourselves. We'll also look at some computing tools for that. And also, we're going to learn what a conservative vector field is, although there is a section on conservative vector fields coming up soon. So we don't do everything in this section. We just kind of we're going to look at the definition. Okay, so what is a vector field? Let's go ahead and get started. This is a question. What is a vector field? So basically, a vector field is a function that assigns a vector to every point in either the plane or in space, right? Because we could be doing this in 2D or 3D, and we don't really know which one it is. I mean, it's not defined, right? So some problems are 2D, some are 3D, and that's fine. So let's look at what is a vector field here. I think we can find a picture of one or two or three or something. I'm just scrolling now. Oh, there we go. Wait, why isn't that in where it goes? Oh no. Oh no, it's here somewhere. I just have to scroll for it. I saved the picture in the wrong way, so now I have to go looking for the picture. You know how it is. Almost. There it is. Picture from 2015, it says. They were sorted by date, but since I saved the picture instead of screenshotted the picture, it got its original file date. Terrible. Okay, so here we go. So here's an example of a couple of vector fields. So what you see is all you're looking at here is that at every point in space, they're drawing a little vector, right? They're not drawing it every point of space because you wouldn't be able to see it. They're only just picking some points in space and drawing the vector there, but you get the idea. So at each point, you're drawing a vector. And so I think what this first picture is this is a plot of, I'll say the force of gravity, net force of gravity maybe, at each point in space. Although again, they're drawing it in a 2D picture here, just because the relationship between the two objects in space is as it is. So what this is showing you basically is probably well, I guess it wouldn't be the path that it would take, an object would take. It would be the force acting on the object. But if you can kind of think of it as the path an object would follow if it was falling, I guess. So if you were here, you'd end up falling and hitting the moon, right? If you were up here, you would all be attracted to the moon, of course, but you're also attracted to the earth, and so you kind of curve that way. If you're a little bit further away, once you get far enough away from the moon, then the force of gravity towards the Earth is going to be more important, and you'll end up, going that way. And those are just they're just mapping out what is the force. So like if you're sitting right here, you feel a force this way. If you're sitting right here, you feel the force this way. Not very much. That's why they draw it small. And they're drawing bigger lines when you feel a bigger force, and they're drawing smaller lines when you feel a smaller force. Okay. Here you have a function that appears to be showing you, I think, the velocity of water in a river. So this is showing um, the velocity of water flowing in a river. Right? At every point, you have a direction and a speed, so a direction and a magnitude that the water is going. Okay, and so those are example vector fields. You can see why you would be using these in physics a lot, because you actually do need to do things with gravitational fields and electrical fields and things like that in physics. So we use them all the time. So these get used in physics a lot. Okay, you have gravitational fields, electrical fields, and so on. Magnetic fields. Also, you have things like that acceleration and velocity and things like that, of moving objects. Also, velocity fields for, let's say, moving liquids, I would say, for fluids, moving fluids. And so on. Right? So these get used a lot. That's why I say that more of this you can kind of pick up in this class, the better off you'll be. They'll reteach you what you need, of course, in those other classes, but the more you know, the more better off you are. So let's get probably a definition now, mathematical definition. Here it is. It just says exactly what we just talked about, though. So a vector field in R2 is an assignment of a two-dimensional vector to each point. And they say in a subset of R2. So, you don't have to be over the entire, XY plane. It could just be in some section. That's fine. Same thing for 3D. A vector field in R3 is the assignment of a three-dimensional vector. So if you have three spatial variables, then your vector field should also have three variables, right? So it's 2 and 2 or 3 and 3. And that's your definition of a vector field. Okay. So a lot of times what they'll do is for notation, they'll have it like this. So notation, usually vector fields are given as, I'll say vector fields in R2. That's where we're starting with, are given as like this. So you'll say f, it's a vector, so you put the vector symbol over the function name. The input is two variables because, as the definition says, you have to take in two variables, x and y. And then how are you going to describe the output? Well, the output is a vector. So two input variables, and then the output is a vector. And there will be a function to calculate the first point, and there will be a separate function to calculate the second point. The second component of the vector. Okay? And then, or just in the other notation, it is a vector, so you might see it this way. P of x, y, I plus q of x, y, j. right? So that's how they'll be listed for you. Um, and they say um, a vector field is continuous uh, if its functions, component functions, are continuous. So if P and Q are continuous, it's continuous, right? So that makes sense, right? If the functions that make up your function are continuous, then it is continuous. They're not going to ask you if a vector field is continuous, but still, continuous, then you could describe this as continuous. Okay. Now your first task, of course, is going to be, if I give you a function, can you calculate point? Can you calculate the field at that point? So example, um, find the vector associated with the point 0, -1. And then they give you a vector field function here, f of x, y. That should be the vector symbol. They're giving it in the ij notation. So they say 2y squared plus x minus 4i plus cosine x j. Okay, so this is just as easy as you probably think it is, right? You just literally just plug in the number for x and y. So super easy. So you just go f of 0, -1, because that's the point they're asking for. And you just put it in all the x's and y's in the function. So 2, -1 squared plus -1 minus 4i plus cosine 0 j. So you just work this out. You get whatever you get. We have 2 minus 1 minus 4, it looks like, I plus cosine 0, which is 1 j. So what do we get? -3i plus j, I suppose. Uh, did I fail to add? Hold on. Oh, yes, I didn't fail to add. I just plugged in the wrong place. So this was x. Oops. You have an x right here. X was supposed to be 0, but I put in a -1. So let's fix that. So it's just 2 minus 4 there. So -2i plus j. Okay. So, I mean, that's it. There's nothing really to that. Okay. So the next thing you're going to learn how to do is how do you draw a vector field? Okay. So what you have to do is this. Well, let's say what our task is here. Drawing a vector field. Okay. So what you do is this. So it's kind of what we need to do is basically what they did in this picture, but we're going to do it in a very systematic way, right? So at every point in the plane or space, you have to draw a vector. So generally what you do is you will do this. So what we're going to do is just, come up with a grid. I'm going to say also in R2. So come up with a grid of X, Y points. And what I mean by that is going to be like this. So if I draw just a set of axes here, right, you can go like this: 1, 2, 3, -1, -2, 1, 2, -1, -2, like that. And when I say come up with a grid of points, what I'm talking about are these. So you can actually put point at every point on a grid, and there's a lot of them, right? Now you get to decide how far apart they should be or how close together they should be, but you do that, right? So like we did, what did we do? So I plotted like -2, -2, or actually like I did -2, +2. That's this one up here, and then you can do all the ones at +2. So then you could do like -1, +2, 0, +2, dot dot dot. And then when you get tired of those, then you can go down to the next row, which was like -2, +1, -1, +1, -1, 0. Wait, no, that's wrong. 0, 1, 1, 1. You get dot dot dot. Uh, then you can move down to 0 on the y-axis, -2, 0. Dot. uh, you know, eventually you're going to go -2, -1, -2, no, -1, -1, 0, -1, dot, dot. Anyway, right, all these points, all the red dots. Okay, so you come up with a grid of those XY points. Then what you're going to have to do, and this is tedious, but what you have to do is you need to plug all of those points into F. So plug all XY points into F of XY. Right, so this is very tedious. And takes forever. But that's what you would have to do. And then after you do that, then you would go back on your plot, and then at every point you would plot the vector at that point. So plot all the vectors you find in step 2. On your plot from step 1. Okay, so very annoying. But like here's an example of that. We'll do it once, I think, probably in by hand, and that's going to be it. So they say plot f of xy equals x over 2 I plus y over 2 j. Okay, so let's see if we can do this. So let's just put this over here, and I'm only going to go out to 2. 1, 2, -1, -2, 1, 2, -1, -2. Because already that is already a lot of points, right? That's like 5 right there, 10, 15, 20, 25. So you would actually have to do 25 function values in order to work this out. Okay. You couldn't possibly do that really. You kind of want to, I mean, you could, I mean, it's not like possible or anything, but you wouldn't want to, right? So you would just start evaluating them though, like f of like -2, 2 is, I'm going to write it in this notation. So it's x over 2, -2 over 2, y over 2, which is 2 over 2. So that's -1, 1. Okay, so at this point right here, which is -2, 2, right? The vector is -1, 1, which is -1 in the x direction and then down, or -1 in the x direction and then up. So this is actually pointing up like this. Now, something you have to think about is, do you want to draw that vector actually with that length? Because -1, 1 is like, I drew this distance to be a distance of 1. So -1 is here, up 1 is here. So that's the correct length. But you're going to have vectors like getting in the way of other vectors if you always draw them that long. So sometimes they just draw them shorter so the graph looks neater. But you don't have to. So we did 1/25th of our job. So then you go next point. F of -1, 1. So that would be -1 over 2, 2 over 2, right? So that is, well, -1/2, 1. So at this point, it's only over 1/2 and then up 1. So it's like this. So that points in a different direction, right? So then you calculate the next one. F of, let's say, 0, 1. So that would be 0. And then you put in, wait, why did I, hold on. This was actually 2. 2. Sorry. I did put in a 2. So 0, 2 is going to give me 0, of course, 0, 1 over here, which is this. Then you move over, f of 1, 2. So that's going to be 1/2, 2 over 2, which is 1. That looks like this. And then I'm not going to plot the last one, but it'll look like that. So you do one row and then you move down to the next row. F of -2 or +1. -2, +1. So that would be -2 over 2, 1 over 2. Or -1, 1/2, right? So that was this point, right? -2, -2, 1. And then the vector is -1, which is over 1, up 1/2. So it is like this. Okay. And you just keep continuing on in this fashion. I believe what will happen here is I'm going to get the ones that I'm going to show you. Like that. You can keep going for as long as you want. You can do the 0 row. So we can go -2, 0, which is going to be -2 over 2, 0, which is -1, 0. So that right here is straight out this way. The rest of that row will be like that. And then again, you just keep going. You just keep going. And I believe this one, if I did keep going, will look like this. So, I mean, I didn't plot nearly all of these, right? I just plotted some of them. But there you go. And that is how you plot a vector field. Okay. Once you have an idea of what it looks like, you kind of cheat, as you could see. Probably, I didn't know what this looked like ahead of time, so I was able to cheat more than you would be able to. You do definitely want to take advantage of computing resources here. You should understand the process, but again, you are going to be limited in your time and for doing this. So I would recommend that you go to Google, type plot vector field as your search criteria. And, you can try Wolfram Alpha, but this one's okay. You type in your vector field here. So like I could go Ours was x over 2, y over 2, variable 1, x. Like y, I don't know why I have to say variable 1, x. I don't know what that's for. Negative 10 to 10. We only plotted at negative 2, 2. Oh, I guess variable 2. I guess that's for specifying the limits. Never mind. Now I know. Okay, upper limit. And compute. Let's see what we get. Okay. Yeah, right. We got the same graph. Um, they plotted a lot more points, obviously. Um, but of course they did. They're a computer. Now, that was Wolfram Alpha. Wolfram Alpha just gives you the answer. This one on GeoGebra I like. I just click vector fields on GeoGebra. So this is an app. So you can type them in here. You type them in separately. So you'd go x over 2, make big, make big. Okay. A, deleted it. X over 2, y over 2, like that. Um, how do I make it small now? I can't scroll. Oh, that was a mistake. Okay, now I can. So I did like this one. On the iPad, it's not as nice as on a computer. What I did like about this one is like you can tell it how to space out the values in your grid with these X in. And then also you can control how it plots the vectors, like in terms of length with the different sliders. Um, and also you don't have to refresh the page to do a new function. So that's another plotter there. If you need to plot them in 3D, I haven't checked that, but if you check plot 3D vector field, probably Wolfram can do it. Um, well, we can try GeoGebra. Oh, yeah, look at that. That's nice. That is nice. So you would be able to type in your functions here, I think. X, Y, Z. Look at that. Nifty. Now, plotting these in 3D yourself, of course, you're never going to do, pretty much. So you definitely want to find a tool online that will um, help you do this. This one's really nice on GeoGebra here, right? Where you can get a plot, and can just type in your functions for P, Q, and R. There you go. Uh, yeah, that's nice. So do take advantage of those computing tools for plotting vector fields yourself. So see, just kind of a note on types of vector fields. So a radial field, said radial, did not write radial. A radial vector field um, every vector points toward or directly toward or directly away from the origin. So the one that we just plotted was a radial field. Uh, right? Like every one of these vector, oops, I deleted the vector. Every one of these vectors points straight to 0, 0. Actually, straight away from 0, 0, right? Straight away, straight away, straight away, straight away, straight away, straight away, all the way around. That's called a radial vector field. So this was a radial vector field. Okay, so that's just kind of a note. Um, so on another type of vector field called a rotational vector field, every point, sorry, every vector is tangent to a circle centered at the origin. Um, okay, what's the point? Or what does that look like? So what those look like would be like this. I'm not going to plot one in detail, but like if you think about just drawing some circles in here, why did you delete my circle? So the circles that I'm drawing are not the vector field. They're not part of the vector field at all. What they are circles. And the point that I'm trying to make as soon as I finish drawing these circles is that on a rotational vector field, um, every vector on there follows that curve. So like right here, for example, the vector would point straight up. Right here, straight up. Right here, straight up. Right here, straight up. Right here, oh, actually right there wouldn't be any. Um, right? Like, and if you go up, you say like right here, where would it point? It would point this way, right? Right here, where would it point? This way. Here, where would it point? This way. Here, this way, right? It always follows the curve. The vectors themselves are straight, but the direction of the vector is tangent to the circles. Okay, so that is what a rotational vector field is. Obviously, once you see one, you go, yeah, that's okay, that makes sense that that's called rotational. And the names have importance because vector fields that have these properties of being radial or rotational, those have certain properties in certain branches of mathematics. So like a rotational vector field might do certain things if you're taking a fluid dynamics class. Like any vector field that was known to be rotational might satisfy some theorem. So that's why we care. For now, just kind of know what they look like. Um, Radial means out from the center or in towards the center. Rotational means around, goes around circle. Okay, that's just what they are. Of course, you can sketch them. That's not hard because you can go. We're in GeoGebra. Let's look up plot 2D vector field. I know that we didn't type that in last time. We just typed in plot vector field. I'm going to try this other link on GeoGebra. So, okay, well, this is a different one. So here, what's a rotational one? Um, like this, for example. There you go, rotational. It's kind of funny though. If you make the first function y and the second one x, or then you get rotational. And then if you switch them, right, x and y, um, well, you do positive x and y, then you get radial. So anyway, interesting, I think. Um, but doesn't really matter. That's how you plot them. Um, Actually, let's do one more thing as far as plotting goes. So it's going to take a second to find, but I will. So we're going to just instructor cheat. Don't copy my answers, everybody. We're going to instructor cheat until we get past a few of these, assuming they load fast enough to make that possible. Submit. Continue. So I guess we can just talk about what we're seeing here for the homework. So what we saw a few times was like they give you a function. They're just asking you to plug in the point. So just like we already talked about, that's like the first type of problem that we spoke of. Very simple. You're just plugging in the number and getting a number. Same thing here, just plugging in the number and getting a number or getting a vector. Okay, I guess we'll do it in this order. So here's a question. Is the vector field a unit vector field? In order to answer that, we must know what a unit vector field is, right? So let's define it. So a unit vector field is a vector field where the magnitude of every vector in the field is 1. Okay, very simple definition. It's easy to check as well. Um, what you do to check is you're just going to calculate the magnitude of the vector field, right? So to check this, for f of xy, just compute magnitude f. That's it. Um, you have, but like f is a function of x and y. That's fine. You just keep the x's and y's, and somehow they'll just magically go away if it's a unit vector field. Also, once you've done one or two examples, it'll be obvious. So, like, let's try this one here. This one's not a unit vector field. We'll see why momentarily. Is x over 5, y over 4, so 4, f of x, y, a unit vector field? Question mark. Let's see. So you just do this. Answer. Magnitude f is, how, yeah, you have to compute the magnitude of a vector, x over 5 squared plus y over 4 squared, which is simply square root, x squared over 25 plus y squared over 4. Is that always equal to 1? No, right? That's not always 1. So, not a unit vector field. Not a unit vector field. Hard work is paying off. Look, they did exactly what we did. This one's also not a unit vector field. I'm going to go to one that is, and we'll do it again. Oh, they're not going to give us one. If they don't, I'll just make one up. Don't know why they're giving us these again. Those were like what we did at the beginning. Also not a unit vector field. Come on. Give me a unit vector field. Yay, there we go. So that's what one typically looks like. You see those denominators, obviously. That's kind of what you'll have to have in order to be a unit vector field. You'll see why, right? Um, is so f of x, y, 7x 7x. The other one is y. And basically, by the way, if you took the 7x and y just by themselves and you calculated the magnitude of those two, it'd be 7x squared plus y squared, right? And just by coincidence, that's what the denominator is. And by coincidence, what I mean is that's not a coincidence, right? Um, so they say, is that a unit vector field? Yes, it is. How would you figure that out? Again, you just calculate magnitude f. So you just go magnitude f. It would be 7x over square root 49x squared plus y squared plus y over 49x squared plus y squared. So we're doing the same thing we did before, but this time when you square it, you get 49x squared here. The square root disappears, so you get 49x squared plus y squared over 49 plus y squared. 49x squared plus y squared. Of course, you add those up. They're fractions. You get 49x squared plus y squared over 49x squared plus y squared, which is the square root of 1, which is 1. So it is a unit vector field. Okay, of course you can see if something looks like a unit vector, right? Like that looks like they divided a vector by its magnitude, and so that looks like a unit vector field. Technically, you would still have to check, but of course it is. So those are not so bad. Now I'm going to continue on for the ones that I was looking for, which what I'm looking for is where they're plotting three-dimensional vectors. Not calculating them because you already know how to calculate vectors. Okay, they're doing here they're just asking you if this is the correct graph. Honestly, I would just go plot it on a computer or plot a few of them by hand. That's one way to do it. Like if I was trying to do this by hand, like I'm too lazy to graph it, but I need to know the answer to this question here. Like, so like which graph is correct? So this is just off the homework. I'm not going to draw the graphs, so you'll just have to see the video. Which graph is correct for f of negative 2x plus y, I plus negative x minus y, j. Right, and so what you can do is you can just pick a couple numbers and just see what's going on. So like, well, it's hard for me. I can't point at this, but so like, look in the lower left, or sorry, look in the upper left corner here. Upper left, right? So like, you see where y equals 2 is, right? And also we're over at around negative 3. So if you go to like negative 3 or negative 2 positive 3 or negative 3 positive 2, something like that, and calculate the vector, what do we get? So like, let's just compute f of, let's say, negative 3 positive 2. Or even 2, 2. 2, 2 is going to be easier to find. Let's do negative 2 positive 2. Negative 2 positive 2. So if you plug that into your formula here, of course, that's not going to be hard to calculate. Negative 2 plus y, which is 2, I plus negative x, which is negative 2 minus y. I can barely write here because there's like the HDMI adapters in the way. Negative 2 for negative x minus y, which is minus 2j. Is that right? I think so. So you work this out, you get negative 2 times negative 2, which is 4. 4 plus 2 is 6. I. And then on the other one over here, oops, on the other one here, you have negative negative 2, which is 2. 2 minus 2 is 0, right? So you actually get plus 0j. Like, so what's that vector look like, or what's that point look like, right? What this is saying is that if you go out to negative 2, 2, you should see a vector right here pointing 6 in the x direction, 0 in the y direction. So it should be pointing like that, straight to the right, um, right? The vector 6 comma 0. So obviously this first one is wrong, right? Now I look at the second one, and the second one could be correct, right? Like, doesn't that look like the 1 point we calculated? It does. Let's look at the third one. Third one, obviously wrong. What about the fourth one? Do we only have 3? No, we have 4. Fourth one, that one looks okay too, except that if you look at it, they're pointing to the left. They're supposed to be pointing to the right. So just based on the 1 point that we calculated, you can already say it's got to be this one, right? Just from calculating that at one single point. So you don't really need to use a computer. You can get them right just by calculating like 1 point a lot of times. Does it go up? Does it point down? Does it point left? Does it point right? That's going to be all you need. This is how many they plotted to try to figure it out. I'm looking for a 3D one. The 3D ones are right after the 2D one, so we should have one coming up. Ah, we do. There we go. Right, so how would we do this? So let's try this. So I'm just going to say example, see video. Oh, we got the vector field. We have to match it up to the function. Okay, so here's my, so what we're doing is we're matching a graph, a 3D graph, to the function. So my recommendation is this. Try to rotate the plot until you have x pointing there and you have y pointing there. That just makes it easier to see what's going on. So maybe you can see the x, like it's on the left hand side right there. That's what I want. But then I want positive y pointing straight up. So I'm kind of just rotating it. Right now I got positive z pointing up. That's not what I want. I want positive y. Okay. It's hard to rotate. Just let me just rotate a little more. Okay, good enough. But I'm still going. Okay. So on the one that we just plotted here, here's what I notice. That when we're looking at it this way, I'm seeing all of them point down like this to the left. Now I can't rotate it perfectly, but that's what I'm noticing, is that they're all going that way, right? So I see all vectors pointing down and to left. They all look like basically the same length as well, right? Some aren't 0. They're all basically the same length. They look the same length. Okay, now let's consider our choices. So let's consider our function choices. So let's scroll, not that. Well, come on. Okay, there we go. So we got -2 negative 4, negative z. I've got negative 2x, positive 4y, negative z. I've got negative 2, positive 4y, negative z. Then I've got 2x, negative 4, positive z. So one thing I notice like right away on these is that this is negative 2 in the x direction, negative 4 in the y direction, right? So they're all like this. So already I think this is it. Done. Done. Right? I know it's not this one because having the x and the y here means that when x is 0 or y is 0, the vector length, that would be 0 for x, 0 for y. So it wouldn't be down and to the left at x equals 0, y equals 0. So this would not be, so actually none would be down and left at x equals 0 and y equals 0. Some of them would be one or the other, right? Like this is to the left, negative 2 to the left, but here the y would be 0 when y equals 0, which would mean when you're looking at it, you would see vectors of length 0 in along the x-axis, and we don't. They all kind of look the same length. So I'm already done just from that. I just go, okay, well, it's that one. And that's how, like, that's my strategy there. We can try like one more. So again, here's my strategy. Try to get x pointing out to the left, and let's try to get y pointing up. I mean, you could do z pointing up, whatever. Okay, can I? Oh, okay. X this way. Yay, did it. Okay, they're all pointing down to the left again. So it's pretty much the same idea as last time, where they're all pointing down and to the left, and they all have roughly the same magnitude. I rotated too much, but okay, there. All right, so which one does it? So this is wrong because the magnitudes change when the x and the y change. This is wrong because the x value changes in length when x changes. This is going to be right because that's down. That's like negative 3 to the left, negative 2 down, always. This one's wrong because the length of the vector in the y direction changes when y changes. So it's got to be this one. Basically the same problem as last time. Okay, so those are not as hard as you think. You could plot them or do something more complicated to figure that out, but that's how I would do it right there. Let us keep going. All right, I think we're onto our last topic, really. So this is going to be conservative vector fields. Conservative or gradient vector fields. All right, so we need a definition. So very simple. So a vector field definition. A vector field is conservative a gradient field, as we can call it, if a vector field F, sorry, let's give it a name, is a conservative vector field if it is the gradient of another function, scalar function, just call it F, right? So the gradient of f is equal to capital F in that case. So if you're the gradient of a function, then you're a gradient field. Okay. So, like, for example, you could do this. You could say, let f of x, y, could be, x squared, y squared, something like that. Now, you could say, find the gradient field for the little f. Okay. So, again, there's not much work here. Answer. All you're going to do is, it's just the gradient. Take the gradient. Hard part is remembering what a gradient is, right? Grad f is right, the partial fx comma fy. That's what it is. So you're just taking those two partial derivatives. So the partial with respect to x is going to be 2x y squared, right, referring to this function. And the partial with respect to y is going to be, well, the derivative of y is going to be 2y. So we're going to get 2x squared y. There you go. And then that's the answer. But also, by definition, this vector field, 2xy squared, 2x squared y, is a conservative vector field. Or a gradient field, right? Which they're the same thing. Right, by definition. Because the definition of a conservative vector field is you're a gradient of something. Okay, so there's not really a lot to do there as far as that goes. I think they'll probably in the homework just have you calculate some of those. Get past this. Let's see what they do. Oh, another match the graph. Easy peasy. Four of seven objectives. Does it feel like I did four objectives? I mean, I know I skipped past them. Um, Man, there's a lot of those. They're not hard though, right? Um, how do I get hard to rotate to the right direction? Where's X? Okay, X is straight up now. How do I get X to the right? Okay, X is to the right. How do I get Y straight up? Oh, almost. I was so close. Oh, okay. Look at this one. This one's up and to the right now. They're all up and to the right. That's to the right, oh, and down, also changing length. They're changing length in the X and the Y direction. This is to the right and down. This one's to the right and up. Yay, did it. Right? Once you've done a few of those, they're very easy. Oh, okay. So then here is a type of question that you're going to see regarding conservative vector fields. So could the vector field be conservative, right? So right now we don't have a test for conservative vector fields. Okay, so we're going to need a test to test whether a vector field is conservative, right? Because this is saying a vector field is conservative if it is the gradient of another function. But how do you know? If they just give you a vector field, how are you going to know if it's conservative or not? So that's our next task. So um, if you're given a vector field How would you know if it's conservative or not? Okay, and so in order to do that, we're going to need a test. So let's see here. All right, so here's your theorem here for this theorem. So let f be a. Actually, let me give you the idea of it first, but I'll just move this down a little bit. So let f be a vector field uh, with continuous second order mixed partials. Okay, so um, here's the idea. So just recall this fact. Um, for good functions, quote, quote, good functions, with continuous derivatives and stuff, with continuous second derivatives. For good functions, um, if you take the partial with respect to x and then the partial with respect to y, wouldn't that normally equal f of yx, right? It didn't matter. That was a theorem that we had from when we learned about vector valued functions. Um, no, not vector valued functions, but when we learned about functions, we had that idea. And so if you think about it, like when you take a gradient, right? This is f, oops. When you do a gradient, this is fx and this is fy. So what if you just take this and then you do ddx? And what if you do this and you do ddy, right? Then wouldn't, if you do ddy of this thing and if you do ddx of this thing, then this is f of xy and this is f of yx. So they would have to be equal, right? If you do this operation and this operation, you need to get the same thing, right? And that's all this theorem is going to tell us. So we remember this fact here for good functions, f of xy equals f of yx. So if f is a continuous vector field with continuous second order mixed partials, um, then get the color. Then in 2D, right? This is for f in 2D. Then what would happen is, I guess actually they write it slightly different. Let me rewrite it. If f equals p of xy, comma q of xy, um, if that's conservative, then partial of p with respect to y has to equal the partial q with respect to x. And that's because this is already partial with respect to x. So when you do partial with respect to y, this is actually f of xy here. So this is f of xy, and then this is f of yx. Okay, so because these are already the derivatives of something, then if you take one more derivative, it's a second derivative. So this is f of xy, this is fxy, this is fyx. They'll be equal if it's conservative. Now in 3 dimensions, it's a little bit more complicated. So if f is t xyz, q xyz, r xyz, then you still have the same kind of theorem, but there's just three different things that could be equal, right? Because there's like fxy, fyx, fxz, right? Fzx, fyz, fz, whatever, there's six. There's a bunch of mixed partials. So if this is true and f is conservative, then, the relationship would be slightly different. Py, that would be fxy, would have to equal qx. That would be fx. So this one's fxy and this is fyx. The other condition that you need would be that, right, you'd have fxy equals fyx. You'd also have to have fxz equals fzx. And then also you'd have to have fyz equals fzy, right? All three of those would have to be true for the mixed partials to all, satisfy that theorem. So we just did one of them. The other one is qz. So that's the last one, yz, would have to equal ry, and then also rx, that would be the zx integral, would have to equal ez, which would be the xz integral. No, derivatives. How many times did I just say the word integral? I don't know. Hopefully not a lot. Right, so these are just mixed partials equal, mixed partials equal, mixed partials equal. Okay, and so it's just from that idea. So this is just because, right? So I'm not going to do a proof, but the proof is basically simply if f of, let's say, xyz equals pqr is conservative, then f is actually fx, fy, fz. So, provided we have the continuity condition, so if that satisfies the continuity requirements, then, fxy has to equal fyx, which fxy would be py, and fyx would be qx, and fxz would have to equal fzx, which would be fxz would be ez, that would have to equal rx, and then f of xy would have to equal, no, we already did that, f of yz would have to equal f of zy, which would be qz has to equal ry. And these would be just these, but written in the other notation. So I said I wasn't doing the proof, but really I did the proof, except I just not super rigorously in my vocabulary there. But that's it. So that's fine. So that's what you would use to show that something is not conservative, or yeah, something is not conservative basically. So if you were doing this here, you would simply calculate these partials and see which ones worked out. So could f negative y squared z negative xy negative xy be conservative? Right? We would just look at the partials. Right? So if you do partial p with respect to not x, we don't need that. If you do partial p with respect to y, here's p. So take the partial with respect to y, it'd be negative 2yz, right? That would have to be equal to qx. So take the partial here with respect to x, that's going to be negative y. Um, are those equal? No, right? Theorem says that they would be equal if it was conservative. So not conservative for sure, right? So there's no way that this could be the gradient of a function because it doesn't, partial derivatives don't work. Okay, so that's not that bad. More of those. I'm sure we're going to have to do what they call finding the potential function soon, so I'm going to get to that. Oh, there's finding a gradient field. That's just taking derivatives. That's good. Another one of those. That's easy. Another, could it be conservative? That's easy. Could it be conservative? That's easy. We're just trying to get to one before I go back to do the last theorem. Well, how could it be? I feel like not finding the potential function anywhere. Okay, well, we're still going to do it, even if it's not in the homework. Should be in the homework though. Huh, we didn't do it. Okay, well, we're still going to cover it. Um, so um, let us do it. So let's see. So if a vector field is conservative, it is the gradient of a function, right? That's the definition. Little f. Um, so there is a way to work backwards and find the little f. So we call, let me just move this down. So the relationship is this, right? That if you take the gradient of little f, you get the vector field f. Okay, so we call the little f the potential function. Okay, so that's important. The name of it gets used a lot. So we call f the potential function. And you can find it. It is possible to work backwards and find the potential function. Okay. Now, apparently, it's not in the homework. I'm sure it will be in the homework a couple sections from now. So let me see if I can do one. Oh, it's just, I guess it's not in the homework. Okay. Well, sort of disappointing. I'm honestly a little bit sad, right? We can do it. Um, all right. Well, they do put it in the notes, but that they don't put it in the homework. Okay, I'm going to tell you now, and then probably you're not going to do it on the homework until later. But here's what you would do. So let's just do one example, and we'll probably be doing it again 2 sections from now. Okay, so suppose we're given, let's say, no, not gradient f. Let's just say f equals, and it's some function, and it's supposed to be it's going to have to be conservative. So I'm going to have to think of one. I'm going to go 3xy squared. And then let me think about what the y would have to be. If I take the derivative of what I just wrote there with respect to y, I get 6xy. So if I do that, if I take the derivative of that with respect to x, I just get 6y. Is that going to work? Yeah, that's going to work. It's going to be kind of too easy, but we'll do it anyway. Okay, so suppose we're given this and told that it's conservative. So we don't have to test it, we're told it. Okay, they could ask you, they say, what is the potential function? Okay, and so what you do is this. So, idea. If you have this function, which is 3xy squared, comma 3x squared y, is supposed to be the gradient of something, right? It's supposed to be the gradient of f, which means it's fx, fy, right? So fx is apparently 3xy squared, right? So if you wanted to know what f is, you would integrate with respect to x, because this is the derivative with respect to x. So this says that um, you know, well, I don't want to say that. This says, no, since the partial of f, partial derivative of f with respect to x. So if you integrate with respect to x, you would work backwards to f. Would get you back to the little f. Okay, that's the idea. So you do that integral. So you do the integral of 3xy squared, and you do it with respect to x because that's what it was the derivative of. So we integrate with respect to x. So if you are, wait, is that the correct one? Yeah, okay. Yeah, okay. So you integrate this with respect to x. So you would go 3x squared over 2y squared, right? So you end up with 3 halves x squared y squared. However, you would get plus a constant, right? And the thing about that constant is that the constant is not actually a constant. The constant could actually have functions just of y in there, right? So let me say that. So this is not, oops, that is not really a function. Sorry, it's not really a constant necessarily. Um, the plus c is actually any function just of y, because when you do like partial with respect to x of f of xy, um, any function just of y, the derivative is 0, right? The partial of a function of y is 0. right? Like when you do this, partial with respect to y of, let's say you do sine y. That's 0. Sorry, now it's 0, right? When you do the partial with respect to x of sine y, you treat the y like a constant. So this is a constant, so its derivative is 0. So instead of writing plus c here, you should write like plus c of y. So like c is a function of y, right? So use c of y to show that it can be a function of y. Okay, now you do another integral, right? The other term was here as well, right? Um, Also, we know that fy must be that other function, which was very similar looking, but 3x squared y was a little bit different. 3x squared y. So integrate that with respect to y, and that would also get you back to f. Okay, so that also will get you back to f. So you do that integral, well, you do this integral, a new integral, again. So you do the integral of 3x squared y dy. So when you integrate that, the antiderivative of y is y squared over 2. So you end up with 3x squared y squared over 2 plus a constant. But this constant could have x's in it. Call that one C2, and I'll come back up here and I'm going to call it C1. Okay? And the point of this is that this is what f was equal to. And the point of this is that this is also what f of xy is supposed to equal to. So what we actually came up with were two different formulas for f. So we just came up with two formulas for f of xy. They are f of xy is equal to, the first one was 3 halves x squared y squared plus c1 of y. And the second one was f of xy equals 3 halves x squared y squared plus constant of x. Okay. And then basically what you do is every term that appears in both of these, every term that appears in one of them or the other must appear in your answer. Um, so what you do is combine them. So to combine them, what you do is this. Every term that you see in either formula for f, because you have two formulas for f, and they don't have to be the same. They look the same here, but they don't always look the same. So any part that you see in either one of them is actually part of the real f. Don't leave any out. That's the key. So for us, so we would just have f of xy. We only have the one term, 3 halves x squared y squared, right? That appears in both formulas. And then we got constant that's a function of y, constant that's a function of x. Then you could just say, well, let's just have any constant. And then that would be that's what you would have. Okay, and just as like an example here, let me Find the gradient of another function. I'm going to do it on a computer that you can't see, just so I can show you one. Gradient. Okay, perfect. Perfect. So this will be our final example and then we're done. I'm just going to say find the potential function. So there is a potential function, which means I am giving you a gradient field. Uh, oh, oops, I did this wrong. I did not type in what I meant to. This will work. I'm sure it will work. Yeah, perfect. Okay, so here's an example. So here they don't look exactly the same this time. So I just couldn't think of one like that when I wrote the other one. So same strategy. So the same strategy. The strategy is simply this. This must be fx. This must be fy. So we just integrate them appropriately. So we integrate. So f of xy must be the integral of fx dx. So we integrate with respect to x, y cosine xy plus 2e to the 2x with respect to x. Okay, so let's do that integral. It's not as hard as you think. We're doing antiderivatives here. So we're treating the y like a constant. So the antiderivative of cosine xy, like remember how this would work, right? Like if that y was like a 2, right? You would just go, the antiderivative of cosine is sine 2x, and then you would divide by 2, right? And if you change that 2 to a y, change the 2 to a y, then it would be y. And so that's what you do here. So the antiderivative of cosine xy is sine xy over y. So you get y sine xy over y plus you do the antiderivative with respect to x of 2e to the 2x. That's 2e to the 2x over 2. And then like we did on the previous one, the constant could have any amount of y's in it. So you just put c of y, c1 of y maybe. Okay, so we get this. You can, simplify a small amount, just cancel the y's. So you get sine xy plus e to the 2x plus c1 of y. Okay, now you do the same thing for the other one. So also f of xy must be the integral of whatever the fy is with respect to y. So you have the antiderivative of x cosine xy dy. So we do this integral. Same thing is going to happen. The antiderivative of cosine xy is going to be sine xy. Then you're going to divide by the constant, which is x. And then we have plus a constant, which is going to be another function, c2, that could have any amount of x's in it. So what do we get? We get sine xy plus c2x. So you look at them together, right? This says, so combining them, we have one of them said f of xy. I'm just going to write the one we can see first. Should be sine xy plus c2 of x. That's just the one that's on the screen. The other one said sine xy, that was the same, plus e to the 2x, that was different, plus c1 of y. Okay? So for your final answer, you just take any term that appears in either one. Take all terms that appear in either. So you would say f of xy is going to be, right? So what you do is this. You say, okay, well, this has got a sine x. So we need a sine x, y, sine xy, right? Also, we have an e to the 2x, right? This one has an e to the 2x. This one does not have an e to the 2x. But really it does. It's just that because e to the 2x has only x's, the e to the 2x here is actually part of this constant, right? Because it's not really a constant, it's a constant function of x. It's got x's in it. So this is actually part of this. But it doesn't matter. What you need to know is that this appears in both, this appears only in one of them, but we still need it to be part of your final answer. So you just take them both. And then you only need a regular constant once you do that. So does that make sense? You just use this and you use this because that's all of the unique terms from either formula for f. And that's how you come up with a potential function. You can do it for 3 variables as well. You just have a third function to integrate, and the rule is the same as far as how to combine them. Okay, so I think that's it for now. Good luck on the homework for this. Should be very straightforward, I think, compared to some of the previous sections. Some of them recently were pretty difficult.